Hello and welcome to your new course, and congratulations for taking the very first step to become a professional embedded systems engineer. In the next around 19 hours of lecture material, we will journey through all aspects of software development for the AVR microcontroller, which is widely spread and commonly available in form of Arduinos. And here are the major topics we are going to cover. The topics are organized in chapters, and you can take the chapters in order of your interest and needs, as most chapters are independent of each other. If you decide to follow the schedule, then we will start with the GNU compiler collection, and we will cover what every single step in the collection does. And if you're a little bit rusty in C, we also prepared a chapter for you to go through the fundamentals of, for instance, pointers in C before moving on and shifting from the Arduino IDE to the AVR architecture to see what happens under the hood. To make the compilation simpler, we are going to look at makefiles and how they work. That will allow us to reuse them for the exercises that are attached at the end of every chapter. To avoid common mistakes, we will examine how the programs work in C and what happens behind the scenes. With negative examples, I'm going to show how not to write a program in C, which gives a lot of power and hence responsibility to the software developer. And from then onwards, we concentrate on the periphery that the AVR architecture offers. As an example, the ATmega328P is taken, but there are many similarities among the avr MCUs. We will start with timers, and we will not only see how to configure those, but also how they work internally. The same is true for the essential interrupts and all the communication protocols which the AVR supports or even does not, and what to do about that. Towards the end of the course, we will concentrate on removing the Arduino development board to reduce the physical size and system costs. In addition, we will focus on how to save power and will be able to answer questions like a fast clock and a longer sleep, or a slower clock and a shorter sleep. What is more beneficial for my implementation? Therefore, after completing this course, the successful graduate will have the experience not only to evaluate existing software, but also to create implementations which are highly optimized to be deployed on small microcontrollers to squeeze out every quantum of performance and battery life. This course is very practical and follows the motto, learning by doing. Therefore, a bit of hardware is required, which is available easily. First, you will need a PC or laptop or any computer which allows you to develop software. And you will need some tools. For instance, sometimes a flat screwdriver will be useful to break out the ATmega from the Arduino board, for example. And you will need an Arduino, preferably the discontinued Duemilanove on the right or the Arduino Uno on the left. If you go to a store, watch out that the MCU, that is the ATmega328P, which is located here, is not soldered to the board and can be removed. Otherwise, you will need some separate ATmega328Ps. In this course, you will need at least 2 of those Arduinos. Better would be 3. And you will need a breadboard, which allows you to build prototypes in the exercises. Along with the breadboard, you will need some standard components such as resistors, capacitors, some LEDs and wires to connect everything. Maybe your electronics store has some ready-made kits which contain all those already in a single bundle. Also try to get a 5 kilo ohm potentiometer, that is a variable resistor, and some infrared LEDs and photodiodes. Somewhere in this course is hidden a fun exercise where your ATmega learns how to say something. For that, you will need a speaker. A cheap internal speaker that were in PCs in early days is perfect. And last but not least, you will need a multimeter to measure voltage and current. It would be nice if the amperemeter has a range into micro and maybe even nanoampere. But do not spend too much on those if you need to get one. There is no upper limit for multimeters. So in short, here is the complete shopping list. Of course, if you do not have the equipment right now, you can skip the exercises for the time being. They will still be there when you decide to come back. This shopping list is also attached to the resources folder, so you can take a printout and take it with you to the store. And that was all about the required hardware. Let's see what software you will need. Obviously, you can use the operating system that you currently have. You just need the Arduino IDE installed, which comes with everything that we need. Although, we will not use the Arduino library later in the course. If you cannot install something on your machine, I am also providing a VirtualBox image with all software already pre-installed. The operating system in that image is the Linux distribution Ubuntu. To make use of the VirtualBox image, go to the website of VirtualBox to download the required software for your operating system and install it. At the same time, go to the link shown here and download the image. All links are attached to the resources folder on the right. I'm also going to attach a PDF in which I noted down some problems and solutions you might run into when using the image. And you will need to have the ATmega datasheet somewhere close, as we will refer often to it. It is attached here, but also later you will find it in the lectures. And with that, you are all set and ready to go. Let me introduce myself. My name is Alexander Fell, and this course is a private project that I started about a year ago. It never completed somehow, and is still not done as I keep adding new topics and new discoveries to it. I was always interested in figuring out how the world works. After finishing my PhD, I taught courses in embedded systems, FPGAs, and maker projects at the Indraprastha Institute of Information Technology in New Delhi in India, in a course called Embedded Logic Design for many years. There, I was involved in projects involving everything containing some embedded system, from autonomous cars to remote helicopters. In this institute, I started to develop embedded systems on a more professional level. Some of those systems were deployed in Antarctica to monitor nesting behavior of local birds. The low temperatures and lack of light in the winter months are challenging, especially if it comes to the power supply. Later, I shifted to the Nanyang Technological University and Singapore Institute of Technology, where I worked on software security and computer architectures and started to explore robotics. But right now, I'm in Barcelona at a supercomputing center playing with the big machines. That's about my professional life. More information is on my LinkedIn profile. The link is attached. I believe in feedback and lecturer-student interaction. Nobody is perfect. So if you find an error or bug in a lecture or have a better idea, or you absolutely do not like something, let me know. Maybe I can do something about that to make you and every following student feel more comfortable. Let's discuss. And I'm always looking for your results and achievements.